let us, okay. So we will discuss about these numerical 10 marks, very 10 marks question, important question. That is, yeah, steady state heat conduction through single layer wall, or we can say a plane wall. Steady state heat conduction through a plane wall, or we can say single layer wall. So before that, let us discuss what do you mean by steady state. Thing is, steady state heat conduction through a plane wall. Plane wall. What is plane wall? Means single layer wall. Single layer wall. This is the 10 marks questions. Okay. So one derivation is there. So we'll discuss the derivation is very much simple. Only the simple integration and simple derivative is there. So that is very much simple for 10 marks. But let us understand the basics of this thing. So what is this derivation is about? First thing is we'll break it. We'll break it into three parts. First thing is a plane wall or single layer wall. Okay, plane wall or single layer wall. Single layer wall means what? This is a solid material made up of a single component. Made up of single component. Okay, made up of single component. The example is what? Copper. One copper slab, or you can say copper brick, slab or brick, or you can say a wood brick, or you can say steel brick. Okay, brick, you know, brick or slab we are using. Okay, it means a solid structure. Okay, that is generally called plane wall. Plane wall means what? Solid wall and a single component made up of single component. That's why it is called single layer wall. Okay, this is first thing. Next is heat conduction through. It means through this wall or solid wall, how the heat will conduction. How the heat will flow? Heat will flow through conduction only. Why? Because this is a solid wall. This is a solid wall. So heat will transfer through conduction. So the thing is heat conduction through a plane wall or single wall. Suppose we will consider a plane wall or a single solid material. How the heat will transfer through conduction. That is the derivation is about. Okay, then another term is steady state. So before going to before going to this derivation, let us take some time to discuss what do you mean by steady state. Okay, so three definitions are there. First one is equilibrium state, unsteady state, and steady state. These basic concept is you have to state means what? Condition. Okay, so these three conditions you have to understand for every material during heat transfer. These three conditions will be there. First thing is there. So how we will define these three conditions? These three conditions will define according to time and position. Okay, we'll discuss. Okay, don't worry, just give me some time. So, okay, so heat conduction through a plane wall. It means what? A single wall or solid wall will be there through which heat is transferring. How? Through conduction, because it is a solids. So how the heat will transfer? The heat transfer will with the three stages will be there, or three conditions, or three different categories will be there, or three different stages will be there. That is that equilibrium stage, equilibrium state condition, unsteady state condition, or steady state condition. How will define? This thing will define according to the time and position. How? Suppose say, let us consider a solid object. Kindly listen it carefully. Okay, Saka condition is solid object. Then initially the temperature is at 30 degrees centigrade. Let us take this this position is 0 centimeter, 1 centimeter, 2 centimeter, 3 centimeter, 4 centimeter. Okay, this is the centimeter. In centimeter, the distance is there. The all object is now at 30 degrees centigrade. So suppose say this is, let us take this is the temperature and position scale. So this is 0, 1, 2, 3, 4. So now what is at the temperature? The object temperature is 30 degrees centigrade. And suppose this is the temperature scale. This is the length scale. Okay, delta X scale. So at position 0, what will be the temperature of this object? 30 degree only.
Yes, sir.
Okay, 30 degree only. Suppose say this is 30 degree. Okay, at point 1, this temperature, what is the temperature of this object? 30 degree. Because now the whole temperature is 30 degrees centigrade. We are not giving any heat source. At room temperature it is there. At point 2, this is a 30 degree centigrade. At point 3, 30 degree. Point 4, 30 degrees centigrade. Yes or no? Just take a time, 1 minute time, and try to understand these things. If a temperature is at a room temperature, suppose say at 30 degrees centigrade, uniform temperature, then wherever position it is there, if you measure the temperature, same temperature will reach. Will observe same temperature. Okay, wherever the temperature, everywhere the temperature will be 30 degrees centigrade. Where if you measure this temperature, this place, and this place. Okay, so this is called equilibrium state. This is called equilibrium state. So in equilibrium state, what is happening? The temperature not changing, or you can say the change in temperature not observed with respect to time and with respect to position. Okay, a little bit hard to understand, digest, but try to understand. So suppose at time t it is at 30 degrees centigrade. Now at time t is equal to 0 minute. What is its temperature? Same 30 degrees centigrade. At time is equal to 1 hour. What is its temperature? Same 30 degrees centigrade, because we are neither increasing the temperature, neither decreasing the temperature. We are not giving any temperature and we are not extracting the temperature. The temperature is always with respect to position and with respect to time. It is always constant. That is called equilibrium condition. Okay. Any doubt till now?
No doubt, sir.
Okay. See, Sanjay, are you there?
Yes, sir.
Okay, okay. Thank you very much. I am glad that you are listening. Okay, so next is, this is all about equilibrium condition, in which the temperature change in temperature will not observe with respect to time and position. Next, suppose say this object is now at 30 degrees centigrade. Everywhere the temperature is 30 degree. Now what we'll do, we will increase the temperature here. Suppose here we supply the temperature, suppose say 200 degrees centigrade. In the same time, what will be the temperature here? 30 degrees centigrade. Suppose at time t is equal to 0. So after time t is equal to 0, okay, what we did is we supply 200 degrees centigrade here at this end. This end means what? At the position of 0. Then what will happen? What will be the temperature of 0? It will be 200 degree centigrade. Yes or no? Because we applied 200 degrees centigrade here. What will be the temperature at 4.4? It will be 30 degrees centigrade. So what will be the intermediate temperature? As the heat will travel, then we can find the temperature here. So at 0 minute, you will find here the temperature 30 only, but here little bit 50 degrees centigrade. Suppose at 5 minutes. So this is at 0 minutes we observe, okay, at 0 minutes, the temperature profile. But at 5 minutes, after 5 minutes, what will observe? We find this temperature will slowly increase. It means what? This temperature may reach 80 degree, this temperature may reach 50 degree, this temperature may 40 degree centigrade, and this temperature, let us say this temperature is 30 degree centigrade only. So at 5 minutes, this is at 0 minute, this is at 5 minutes. Then after, suppose say 30 minutes, what the temperature will reach? Suppose at 30 minutes, what will happen? Here the temperature will reach, suppose say 150 degree centigrade. Here the temperature will reach 100 degree centigrade. Here the temperature will reach 80 degree centigrade. Here the temperature is 30 degree centigrade. This is the temperature profile we observe after 30 minutes. Yes or no? This is the general observation.
Yes, sir.
If you heat any object, slowly the temperature with respect to position and with respect to time, it will also change. So that condition is called unsteady condition. It means what? The change in temperature will observe with respect to time and with respect to position. That is called unsteady state condition. Okay, so take a time to understand these things. Okay, just think about it. In case
Yes, sir,
of,
we are able to understand, sir.
yes, but let others also understand. So in unsteady state means with respect to time and with respect to position, the temperature is changing. Okay, so this is the notes. Let me show you the notes. Yeah, so I will give you the notes, don't worry. Equilibrium condition means the temperature do not change with respect to time and position. There will be no change with respect to time and position. Okay, there will be no heat flow also. Okay, unsteady state or transient state. It means what? Temperature change with respect to time and with respect to position. Okay, and there will be heat flow. In this equilibrium case, heat flow will be 0. Then what is steady state? Steady state, the temperature change with respect to position only. Okay, let me state. Okay, let me give. Okay, sorry. Okay, next let us reach what do you mean by steady state. Same example. Same example. 200 degrees centigrade, 30 degrees centigrade. Now what we will do? If you increase the 200 degrees centigrade, here if you will keep at 30 degrees centigrade, slowly the temperature will increase. Till how much time? Till 0 minute, 5 minute, 30 minute, 2 hour, 3 hour. Okay. If you observe the temperature like that, what do you observe after some time? One time will reach. After that, what we observe is one time will reach. If you increase, if you keep as it is, One time will reach at which you will observe here the temperature is fixed to 150 degrees centigrade, 100 degrees centigrade, 80 degrees centigrade, 30 degrees centigrade. You will find a constant profile. It means what? The temperature will change with respect to position, but with respect to time, it will not change. It means what? You can see, if you give the temperature difference, slowly the temperature, if the time will increase, you will find a temperature profile, change in temperature profile. But after some time, the temperature profile will be ceased, or you can say it will reach to a steady state. What do you mean by steady state in general English? Suppose say one object is traveling from point A to point B. Suppose its speed is 30 meter per hour. Suppose one person is going by bike, okay, and its speed is 30 meter per hour from this place to this place. What we can say? It can say it is a steady state. He is going at steady state. You people are sometimes reading the books without any distraction. So that is called steady state. It means what? Your position is constant with respect to time. With time, your properties are not changing. That is called steady state. But unsteady state means what? Suppose here to here I will go 30, here to here I will go 40, here to here I will go 20, and here to here I will go 60 km per hour. Then what? With respect to time, the position also changing, property also changing. That is called unsteady state. Okay. So what is steady state? Steady state means that change properties is not changing with respect to time, but with respect to position, it is changing. But with respect to time, it is not changing. So steady state means with respect to time, it is not changing, but with respect to position, it is changing. Okay. So kindly keep this thing in mind. So try to digest these things or memorize these things. Equilibrium state, the temperature will not change with respect to time and position. Unsteady state, the temperature will change with respect to time and position. Steady state means steady means what? Anything which is not changing with respect to time. So with respect to time, it will not change, but with respect to position, it will change. The example is this one. Okay. So now let us come to the derivation. The derivation is steady state heat conduction through a plane wall. This is the 10 marks derivation. Kindly listen carefully. Let me change the color of the pen. Yeah. So let us consider a plane wall. Let us consider a plane wall. Let us consider a plane wall. Okay. This is what a plane wall we can take. Plane wall means what? You know, a single layer. A single
Made up of
layer.
single element.
Single layer solid. Okay, solid wall. A single layer solid wall, plane wall. Okay. Suppose say now its length is delta x. Okay. Suppose say this side the temperature is T1, and this side the temperature is this side, this area, this surface. The surface at this temperature is at T2. The surface at this temperature is at T1, and the T1 is greater than T2. Then what will happen? Heat will transfer from the surface A to surface B. Why? Because there is the temperature difference. the heat will transfer from the surface A towards the surface B because the T1 is at a higher temperature, T2 is at a lower temperature. Let us say this is called high temperature surface and this is called low temperature surface. Now, another term is there area. Let us say this area is called A. This is just a 2D diagram, okay, 2D area. So just imagine it as a 3D. So what will happen? What is the heat transfer area? We told heat transfer area will be always perpendicular to the direction of heat flow. So this is the heat transfer area direction. So what is this perpendicular direction? This is the perpendicular direction. So this area, you just imagine is the 3D diagram. This area is called heat transfer area. This transfer area. Okay. So this is what first thing is, this is a plane wall. This is the plane wall conduction. Then we are transferring the heat because the temperature difference is there. How the heat will transfer? Through conduction. Why? Because this is a solid wall, plane wall, solid plane wall is there. Then we assume that it is a steady state. Let's assume heat flow in steady state. Heat flow in steady state. Another assumption we will take what? One directional heat flow. Why one directional heat flow? As you know that if you heat some here, the heat will go all the direction. Okay, but for our derivation, we assume that let the heat only travel through this direction. All other directions are adiabatic in nature. All other directions are adiabatic. Okay, so heat will only travel through this direction only, from temperature T1 to temperature. As per real, the temperature will travel to all direction if a heat source is there. But we assume that all this area is adiabatic and heat is transferring through one direction only. Next, let us assume, let's take another assumption that plane wall is homogeneous. Homogeneous means made up of one component and isothermal. Isothermal at T is equal to 0. At initial time, let the temperature is constant. Okay. Then, according to, okay, from this time, the derivation will start. Kindly listen. Then which law will apply here?
Fourier's law.
Yeah, because we are discussing about conduction. According to Fourier's law of heat conduction, what we'll observe is Q equal to minus K A dt by dx. Is it okay till now?
Yes, sir.
Roll number 9, Tejaswini. Are you listening? Chikita?
Yes, sir.
Okay, please, Chikita, are you listening?
Yes, sir.
Okay, thank
Yes,
you.
sir.
So kindly do listen. This is the most important 10 marks derivation. Related to this derivation, another two derivations are there. So if you understand these things, next two are also easily understand. Okay. So according to Fourier's law of heat conduction, for a plane wall, we can write q is equal to minus k dt by dx. So we need to solve it. This is in differential form, so we need to solve it. So we can write q into dx is equal to minus ka dt. Okay, so in differentiation, what you know, dy by dx means what? Y and x are both the variables. So we need to solve the variable separation method. You know that variable separation method to solve the differential equation. So we'll solve that two. We separate the two variables. So q into del x is equal to minus ka into delta t. Then what we have to do? Differentiation is there means, anyone remember variable separation methods? To solve the differential equation, mathematics. Okay, if not, then kindly listen. So the differential equation is there, so we need to solve it. So first thing what we'll do, first we go for variable separation. It means what? We'll separate the variable. In differentiation, dy by dx is what? Means y and x are variable. Change in y with respect to change in x. Here is also change in temperature with respect to change in x. Okay, so dt dx. Here you can see now the temperature and delta x is constant. The delta x, area is constant, k is constant, heat flow is also constant because it is a steady state. So only difference is delta t and delta x. So next what we have to do? We have to do apply integration. Applying integration. Applying integration. What will be the value? If you apply integration, q into dx is equal to minus ka dt integration. So in integration, you know, we have to put the limits. Okay, so in delta dt. Okay, so this is the what we put integration. So in integration, we know that we generally put the constant term outside the integration. Okay, we'll put the constant term outside the integration. Yes or no? Generally. So here I can write q into integration of del x is equal to minus ka into integration of dt. You can ask me why. Here area of the object, heat transfer area of the object, it is always constant because this is a physical object. Okay, it will not change. What is k? It is the property of the material. These are constant. Okay, so I will keep it outside the integration. Then why q? I keep why q is constant? Because we assume it is a steady state. Okay, we assume it is a steady state. Steady state means the rate of heat transfer will constant. Steady state. We assume it as a steady state. Steady state means the rate of heat Q will be constant. Okay, or the rate of heat transfer is constant. Okay, so next. So what we can write, Q integration of dx is equal to minus k a integration of dt. So let me put the limits 0 to x. Here the limit will be t1 to t2. Limits means what? What is the lower limit? What is the upper limit? What is the lower limit? What is the upper limit? Here you can see that lowest the temperature is from t1 to t2. Okay, here temperature is, suppose say this is a 0 distance, this is the x distance. So we can put the limit 0 to x and t1 to t2. Okay, just a minute. Yeah. Okay, any doubt till now why we put 0 to x and t1 to t2? Because we have to put the lower limit of x, upper limit of x, lower limit of t, upper limit of t. Okay, next we have to do the integration. Can you do the integration of this one? Anyone? What will be the integration of this one? Can't say simple integration. Okay. So generally, some integration, we have some function of x and dx. Yes or no? This is the standard orientation of any integration we are doing. Yes or no? But here such orientation is not there. So how to do the integration? Generally, we are doing integration like that, f of x dx. Suppose say x square dx, okay, or 1 by x dx. Like that it will be there. So these are what? This is function of x. Okay, function of x. Then only we are doing integration. So here no such conditions are there. So then how to do integration? Then what we can do is we can put a dummy f of x. Dummy f of x means what? We can write it as, kindly listen carefully. So we can write it as x to the power 0 into dx, 0 to x. Here what we can write, minus ka into t to the power 0 dt. Okay, so what we did is, to do any integration we required function of x dx. Here we required function of t dt. So previously we find that the dt was there, but the function of t was missing. It is not there. So what we did is we put a dummy of f of x or dummy f of t. What is that f of x? We use x to the power 0, we put 2 to the power 0. What is the value of x to the power 0? 1. What is the value of 2 to the power 0? 1. Anything to the power 0, it is what? 1 only or not?
1,
5 to the
sir.
power 0, 1. 100 to the power 1000 to the power 0 is always 1 only. Anything to the power 0 is 1. So writing x to the power 0 dx, or writing dx 1 into dx, or writing simply dx, does it any change? Does it make any change? No. Here also,
No, sir. The value will be the same.
yeah, t to the power dt, or we can say that 1 into dt. Okay, or we can say simply dt. These three things are same. But why you put t to the power 0 or x to the power 0? To solve our integration. Okay, so what we'll reach is, let me write once again. So what we reach is q into x to the power 0 dx. To solve, we put this x to the power 0. It will not change in the equation because x to the power 0 is 1, and multiplying 1 is not a issue. It will not change, not bring any change to the equations. Okay, so this is our derivation now. So what will be the next step? Can anyone say? Q into
1 dx.
okay, very good. So not 1 dx will be not there. So x to the power n, we have the general formula for integration. So kindly revise the integration, okay, at least the basic formula. So what will be the integration of x to the power n dx? Anyone? X to the power n plus 1 by
N plus 1.
n plus 1. Okay. What will be the derivation of 1 by x dx? Ln x. Okay, kindly remember these things. Okay, don't worry. If you don't remember, just remember. Okay, kindly revise. Okay. So x to the power n dx is x to the power n plus 1 by n plus 1. What is the n here? 0. So we can write x to the power 0 plus 1 by 0 plus 1. What is our limit? 0 to x. Then minus Ka. What I can write here? T to the power 0 plus 1 by 0 plus 1. Same formula, x to the power n plus 1 by n plus 1. Then T2 T1. Okay, then. So let me solve it. So we can write x to the power 0 plus 1 by this. We can write what I can write x 0 equal to minus Ka T T2 T1. Okay. Next step. Next step, what we have to do? We have to open this circle and we have to use these limits. So what we have to do? Q. What I can write here? Here x is the variable. Here t is the variable. Here 0x and t1, t2 are the numerical value. So to solve this, what we have to do? Whatever the variable x is there, first we have to put this limit, upper limit, minus we have to put lower limit. So what is the upper limit? X. So we'll put x here minus. What is the lower limit? 0. We'll put lower limit 0 equal to minus Ka. So here also we'll put first upper limit minus lower limit. So what is the variable t? In place of t, we will put upper limit. What is the value? T2. Then in place of t, we'll put the lower limit. What is the value? T1. And I'm not teaching anything new. Okay, don't amaze. Just the basics solving of integration, just mathematics. Okay, you may solve that variable separation method. If not, then kindly recall the variable separation methods. Otherwise, I am explaining once again. Okay, kindly listen. Then what we can write? We can write Q into this x minus 0. Can I write delta x? Or you can say change in the length. X minus 0 is what? This x minus 0. It is delta x, change in the length. Okay, delta x equal to Ka. Can I write it T1 minus T2? Because minus sign is there, I just put the minus sign inside. So T2 minus T1 will be now T1 by T2. Now, can I write it Ka delta T? Okay, so can I write it as a Q delta X is equal to Ka delta T. Now you see we come to a positive value. Why? Because in place of T2 minus T1, we convert it into T1 minus T2. Okay, then we can write Q is equal to Ka delta T by delta X, or you can write Q is equal to delta T by delta X by Ka. Okay, so next what I can write? Delta T by R. This is the final derivation. And what is R? R stands for, is called resistance to heat transfer, and it is nothing but delta X by Ka. What's its unit? Delta X will be meter. What is the unit of K? Watt per meter Kelvin. What is the unit of area? Meter square. So this meter square will cancel, meter will cancel. So we'll have unit Kelvin by watt. Okay, so this is all about 10 marks derivation. Okay, so if you do this derivation, you will get the 10 marks. So the thing which is important is only simple integration is there. So kindly I revise. Let me revise quickly. Let me show you in the notes. This is the notes I will give you. Don't worry. Okay. So what we did is we take a plane wall. Suppose that T1 is this is T1, this is T2, and T1 is greater than T2. Then what will happen? The heat will flow from T1 to T2. Okay. Let the area of heat transfer is Q because heat will transfer through this area. Let us say the thickness of metal is 0 to X. Okay. Then what will apply? We apply the thermal conductivity equation. Q is equal to minus Ka dt by dx. Or you can write Q into dx is equal to minus Ka delta T dt. Okay. Then what we did? Integration. That is variable separation. Q into delta x is equal to minus Ka dt by dx dt. Okay. Next, we take the integration and we take the limits. What is the lower limit of x? 0 and x. Upper limit for t, t1 and t2. Then what we did? We have to integrate it. So we put x to the power 0 and t to the power 0. Here x to the power 0, here t to the power 0. Okay. Then what will be? Yeah, some technical issue was there. Okay. So 0 to x. So it will be what? X to the power 0, we can write x to the power 0 plus 1 by 0 plus 1. T to the power 0, it will be t to the power 0 plus 1 by 0 plus 1. So t. Okay, and the limits are t1 to t2. So now what we have to do? We have to replace the variable with the limits. So here will be x minus 0. Here will be t2 minus t1. So you can write q into x. If a minus sign will be there, t2 minus t1 will be t1 minus t2. Ka delta t. Then we reach q is equal to Ka delta t by del x or delta t by x by Ka, or we can reach, or we can tell that is delta t by r. So what we reach right now is we can say the rate of heat transfer Q. Rate of heat transfer Q is equal to the driving force by thermal resistance. This is the standard formula. Like V is equal to IR. This is which law? Ohm's law? Yes or no? You know. I think
Yes, sir.
Jivan, am I correct? Yes. Ohm's law.
Yes,
This
sir,
is
yes.
for currents, you know. Then what we can write? I is equal to V by R. What is I? I is the current flow.
Current.
Current flow. How much current will flow? Same like rate of heat transfer, or you can say heat flow. Heat flow. The heat flow will depend on, okay, the current flow will depend on how much the voltage difference. Yes or no? How much the voltage difference is there, the current will flow accordingly. Similarly, what is the driving force? If the temperature difference is high, then the Q will be also depend on directly to it. Then what is resistance? It is inversely proportional to resistance. Resistance means what? The flow, to flow, how much resistance will be there. Suppose say one person is here. Suppose say current is, you are here, okay? You are here, you have to reach to this destination. Okay, you are here. So this is your driving force, or that distance is your driving force. Okay, so here from your home to college, you have to reach. So suppose say it is very crowded place. then what will feel? You will feel more resistance. Yes or no? So the time of travel will be inversely proportional to the resistance. Yes or no? If the resistance is more or crowd will be more, you will feel more resistance to travel from here to here. So you will take more time. The same thing is happening through IR current. If the resistance is more, the current will be flow at less time, or the heat will flow at less time. If the resistance is less, the heat will flow more time. It is inversely proportional. Okay, so then, yeah, just a minute. Where is the notes? Yeah. Then we discuss what is discussed. R is the thermal resistance, that is for X by Ka, or the unit will be Kelvin by watt. Okay, how I will discuss. And the reciprocal of thermal resistance is called conductance. Or you can say C is conductance is equal to 1 by R resistance. This is, you know, in electronics. Conductance means 1 by thermal resistance. So what will be its formula? K by W, just inverse of resistance. Q, you know, steady state heat flow, that is joules per second or watt. K is the thermal conductivity, watt per meter Kelvin. Area of heat transfer, meter square. Thickness of wall, meter. And delta T is the temperature difference in Kelvin. Okay, so this is the formula we reach for steady state heat flow through plane wall. Okay, so hope you people are understand. So lest other things we'll discuss in the next class. I think the time is up. Thank you very much. Let me